Okay, so let's go through the quiz. So last question. Okay. So process number one, 50 millisecond CPU, 50, and followed by an I/O request, of 80, I/O of 80, and CPU of 60, another 60. CPU of 60. And process number two, we have CPU of 30, and we have I/O of 80, and we have CPU of 20. CPU of 20. Okay. So now the timing. Okay, so first we have the kernel for 10 milliseconds. Then the rule is whenever both are ready, give it to P1. So both are ready, so we'll give it to P1. P1 will get that for 40 milliseconds. Then the kernel will get what is in control. Then who gets the CPU? P1 again. So P1 gets the CPU again for 10. Then P1 requests I/O. After 50, P1 requests I/O, so it goes on the I/O device. On the I/O device for 80. So this is CPU, this is I/O. So for 80, P1 goes on the I/O device. Now in the meanwhile, obviously, the kernel doesn't have any choice. It must give the CPU to P2, and P2 will get the CPU for 30. Then P2 will request I/O, but it's requesting I/O from the same device, so it will be queued. And P2 will not get to execute, will not get serviced by the I/O device until P1 is done. So this is P2. This is another 80. This is 80, 80. So, okay. So now the kernel will have the CPU. So this is going to be idle because now the kernel doesn't have any process to give the CPU to. So now this time is going to be 40 milliseconds. Then the kernel will get notified by the I/O device that this I/O request is complete. So the kernel will get the CPU. Then the kernel will look at the ready queue, and it will find only one process on the ready queue. It will find P1. So it will give P1 40. So it will give it 40 milliseconds. Then the kernel will be in control. Then the kernel will give P1 another 20. Then this is 10 more for the kernel. Then P2 will be done, or the I/O device will be done, not P2. The I/O device will be done. It will notify the kernel. The kernel will get control, and it will look at the ready queue. It will find only one process, which is P2, and it will give it the CPU for 20 milliseconds. Yeah.
I think you missed the 10 for the kernel.
10
Between
for the
40 and
kernel.
20.
Oh, this? Oh.
Further,
Okay.
the I/O device should end at the end of
Yeah.
P1.
Yeah, okay, so this is, okay. Okay, so Yeah, you are right. Yeah. So this will end here, then the kernel will be in control. Yeah. So any questions first? Any questions on this? Anything that is not clear conceptually? I mean, anything that is, yeah.
So in general, the entire, I guess the OS has to service the entire CPU request before it can give control to another process. Because if the time quantum isn't enough for P1, you have leftover time. That has to be finished before you can swap it to P2.
No. So where did we do that?
Isn't that what you did? Because P1 got 40 milliseconds, leaving 10 milliseconds left over that P1 needs to finish.
What do you mean 10 left over? 10? Yes, so P1 got 40 because there is a time limit of 40. So that's the time quantum.
Right.
So the time quantum means that the system doesn't give more than 40.
Right.
So even if this was 1,000, then the system is going to give it 40.
But is it going to retain priority until the rest of that time is completed?
No, it's just, this is the scheduling policy that we are doing this based on. So the scheduling policy is whenever P1 and P2 are ready, the scheduler will give the CPU to P1. So this implies that P1 is a higher priority process. It implies that. But see, because we have not covered scheduling yet, so I'm not even mentioning the concept of priority because we haven't gotten there yet, but I'm just giving you the policy. So I'm just telling you what the scheduler will do. And you will do the timing based on what the scheduler will do. And I'm just telling you what the scheduler is going to do in this case. Yeah.
So maybe I'm not coming off clear, but after that first 40 seconds of time quanta is allotted, why does P1 get another 10 seconds as opposed to P2 getting 30 seconds? Because if this is time
Because here
sharing,
the kernel will look at the ready queue.
okay.
To look at the ready queue, how many processes are in the ready queue? P1 and P2.
Right.
They are both in the ready queue. Both are ready. What's the rule? Whenever they are both ready, give the CPU to P1. That's the rule.
So it's still in the ready queue even while it's being serviced.
Yeah, this is conceptually important. Yes. So when a process gets interrupted by the timed interrupt, it will be placed in the ready queue. Right? So this is an important concept. Any other questions? Yeah.
So that last 20 millisecond burst, is that supposed to be P2 or CPU?
Oh, sorry. It's P2. Well, it's P2 on the CPU, but I just wrote CPU. It's P2. Okay. So how many people got this right? About half, less than half. That's less than it was like 60 or 70%. But it's, so what was the difficulty here?
I just messed up because I put P1 and then P2 right afterwards. So P1 for 40, then the kernel time, then I put P2.
But why? Based on what logic did you put P2? That's what I'm having a hard time understanding.
I was being dumb.
No, I'm trying to understand the logic behind it. So
I understand the logic now because I just kind of skipped this policy where it was P1 gets priority if they're both in the ready queue. I was just thinking once P1 uses time up, P2 gets its turn. I just wasn't using
So you were assuming fairness.
Yeah.
You are assuming that the scheduling algorithm is fair. But see, this rule, you know, when we say that whenever P1 and P2 are both ready, the scheduler will give CPU to P1, this implies that the scheduling algorithm is not fair. It implies that the scheduling algorithm is biased. It's giving priority to P1.
I think that when someone hears Q, they think, oh, P1 goes, and then, okay, it's put into the back two,
Yeah.
even though that there's a rule stating that, nope, that's not the case. If P1 and P2 are both in that queue, no matter what, P1 always goes. So I think it's just the word Q that that throws people off, even though there's a rule that states, ignore what you
Okay,
know.
so this is a good point. So let me ask you this. How many kinds of queues did you study in the data structures course?
Two,
What kinds of queues?
priority and just a regular queue.
Well, there we go. There is a priority queue.
Yeah.
Right. So in fact, whenever a scheduler implements a priority scheme, it's going to use a priority It's not going to use a first in, first out queue. So there is a first in, first out queue, and there is a priority queue. That's also an important data structure. And in fact, when the scheduling strategy is priority-based, it makes sense to use a priority queue because a priority queue was just made for that. Tracing a process that is requesting I/O. What are the transitions? There are 3 transitions. First, the process makes the I/O request. It will transition from running to waiting, and it will be in the in the queue for the I/O device. Right? It's not the I/O queue, because when you say the I/O queue, it implies that there is a single I/O queue in the system. It's not a single I/O queue. It's the I/O queue for that device. But then this is a minor detail. Now, what will happen here? What's the next event? I/O completion. The next event is I/O completion. With I/O completion, the state will change from waiting to ready, and then it will be in the ready queue. Okay. Then the third event is the scheduler dispatches that process, and it will change from ready to running, and there is no queue. Oh.
So Professor, if I did I/O interrupt, is that the same as I/O completion?
Yes, but completion is clearer. Yeah, because it's the completion of the I/O. It's just try to be as clear as possible. So let's do question 2. The length of the time quantum given to each process by the scheduler in a time-sharing OS must be selected carefully. What's the negative consequence of making this time slice long, and what's the negative consequence of making it too short? So what's the negative consequence of making the time quantum too long? Yeah.
The process finishes early, then it's just the CPU isn't doing anything. It's waiting to.
No, this is a fatal mistake. This is a fatal mistake. Like, when this process finished the 20 milliseconds, does it take the entire time quantum? No. So you're missing an important concept. If a process finishes, then the kernel will get the CPU. Yeah.
A user might perceive it as being slower, even if that's not necessarily the case.
Yes. So from user point of view, it will feel slow. The user will feel a delay. That will feel that the system is slow because processes are getting long time quantum. So it's from user experience, user responsiveness. So it's negative from user responsiveness point of view. But if the system gives the process 100 milliseconds of time quantum and the process only needs 10, it's going to get 10, and then it will, the kernel will be in control. Okay. Now, what's wrong with making this too short?
Kernel spends too much time on the CPU. Context switching.
Okay. Yeah. So if we make it too short, then there will be a lot of time spent in the kernel, a lot of kernel overhead. Okay? So we will be wasting a lot of time in the kernel, as opposed to use too much context switching, very frequent context switching, so there will be a lot of time spent in the kernel. So one of the wrong answers that I have seen in the past, some students would say that if it's too short, then the process will not get enough time to complete. That's a wrong answer, because the process will always get as many time quanta as it needs in order to complete. So making the time quantum short doesn't mean that the OS is going to cut a process. It's going to terminate a process. Remember that an operating system never terminates a process as long as that process is well behaving. So I'm having this process right now. This is Microsoft Word. If I leave this for a month or 2 months open, the OS is not going to say, I got sick of this process. No, it's not going to say this. I can leave it as, for as much as I want. And as long as it's behaving well, the OS is not going to terminate. Okay. Monolithic versus loadable module. Advantage of monolithic versus loadable module.
Monolithic is potentially more efficient because it has the least overhead.
Okay, so this is vague. This is not clear. So I'm giving you 3 lines to give me a clearer answer.
Faster?
Yeah, so the word overhead is very vague and generic. So there are different kinds of There are different kinds of overhead. Yes.
So it's faster because all its functionalities are in the same address space. So, for example, a user program has direct access to.
No, that's a mistake, because even in loadable modules, they will be in the same address space. So in both, they will be in the same address space. It's faster because, monolithic is faster because, yes?
No message passing?
No, that's another mistake. Message passing is in microkernel. It's not in loadable module. But it's faster. This is loadable module, so it's going to be loading modules, right? So it doesn't have to load modules when it's running. So that's why it's faster. It's just one piece. And there is no less communication overhead between modules. So when you say overhead, you have to specify what kind of overhead. Yes?
So the reason you just gave, isn't that relevant to it being faster? Because the monolithic doesn't have to load anything.
Yeah.
They're already in the same space, but the loadable.
Not space. They are both the same address space. So, don't imply that in loadable modules, the modules are loaded to a different address space. No, that's not true. They are loaded into the same address space. So it's not about the address space. It's about the loading itself. When you load, that takes time. Right?